All right, thank you everyone for coming. So we'll get started. We have today Dr. Vincent Russo, who is the CEO and co-founder of Modelicity, a company that provides software solutions to clients. And he holds a PhD in computer science from the University of Waterloo. And his research is in convex optimization and quantum information. And he's the creator and main developer of Coquito. Did I pronounce that right?
Close enough.
How do you pronounce it?
Taquito, kind of like the dish. Yeah.
Dish. It's an open source library in Python for the study of quantum information. So today he's going to be talking about a conjecture on quantum science. So the floor is yours, Vincent.
Awesome. Thank you for the intro, Curtis, and it's really great to be able to talk to everyone today. This is fantastic. So yeah, like Curtis mentioned, I'll be talking a little bit about quantum information. And one of the things that I'm not really expecting from anyone here is to have any kind of formal background or knowledge about quantum mechanics or quantum information. I'm hoping that the context of this talk will be fairly self-contained. So all of the concepts and things that I'll be speaking about should be parsable and understandable if you maybe have some background in linear algebra. Oh, by the way, am I coming through okay? Is everything vocally okay? I can be heard?
Yeah.
Great. Okay, great. If there's anything that changes, try and either flail your hands or try and tell me to stop or whatever it happens to be. A little bit different when you're not giving talks in person, I understand. So, and I should also say that if there's any questions throughout, please feel free to interrupt me and stop me or save the questions till the end, whatever you prefer. So, okay, this is going to be a fairly self-contained talk, and it's going to pertain about this conjecture, which is called this antidistinguishability conjecture. So it's a conjecture about this concept of antidistinguishability, which is sort of a property that a set of quantum states can have. So we really need to unpack that a little bit. We need to figure out what is a quantum state, what is a collection of quantum states, what do they represent, what is this notion of antidistinguishability, why is it useful, why is it interesting, and then what is the conjecture itself, and what does that conjecture actually imply if it were true. So we're going to actually show that this particular conjecture, the phrasing of it, is not true. And one thing, I know this is a CS Colloquium, so this is we'll have like a live code demo of like a Jupyter notebook, some Python code to show that the conjecture is not true, which might be kind of fun. Live demos, things tend to go wrong, so we'll see if that also happens here. But in any case, we'll go through that. We'll step through the conjecture, what the takeaways are of it not being true, and then maybe talk a little bit about what we can do in light of that. So that's going to be the general overview and gist of the talk. And I should say, too, that this is based on some joint work with myself and Professor Jamie Sikora, who is faculty at Virginia Tech. The archive posting for the paper that I'm going to be discussing in this talk is listed there. So if you want to check it out, it's a pretty short paper. It's just, only a few pages. So I think it's pretty parsable. So yeah, check it out if you're interested. So let me move on here to the next slide. So like I said, I'm just going to kind of introduce just enough quantum information. So I'm not going to expect any kind of formal background. In fact, really, all we really need to do is just think about quantum states in sort of a mathematical framework. So when I say quantum state, really all I'm going to be referring to is just, okay, I thought I heard a question. I'm just going to be referring to a column vector that's living in some complex Euclidean space. For all intents and purposes, for what we're going to be discussing, that's how we can view and visualize quantum states. So one thing that you'll probably see if you open up a quantum information textbook or if you read some quantum information papers is you might see this funny notation, this line and an angle bracket with some symbol in between. So this is known as Brocket formalism. It's basically a very convenient way to describe and write down large systems of quantum states. This was kind of a formalism that was introduced in the early 30s by Paul Dirac, who was one of the founders of quantum mechanics. And effectively, since quantum states, as you know, represent vectors, writing those down in full completeness can be quite cumbersome. So this Dirac notation is really just a formalism that's allowing one to easily write down a number of quantum states that might compose a larger system. So basically, anytime you see a symbol that looks like this just represents a column vector that lives in a complex Euclidean space. And then anytime you see a flipped symbol like this is basically just the same column where we've performed a complex conjugated transpose on that column. So we basically just taken that column vector, we've conjugated it. So all the entries are complex conjugated, and then we transpose the vector. So it's a row vector now. So that's pretty much all we'll need for what a quantum state is. The next thing that we'll talk about is what you can do with a quantum state. So in much the same way that we discussed quantum states, we can kind of visualize some action performing on a quantum state as a completely objective mathematical entity. In this case, we refer to this as a measurement. You can apply a measurement to a quantum state. And a measurement, in essence, can be described by a matrix with very specific properties. So specifically, a collection of measurements, which we can label from M1 to Mn, are some collection of matrices that are one, positive semidefinite. So that just means that all the matrices have eigenvalues that are greater than or equal to 0. And then also, if you take those measurements and you sum up them, you'll basically just get the identity matrix. So if you have those two constraints, those constitute a valid collection of measurement operators. And there's an interesting rule that won't be taken advantage of, which is known as Born's rule, named after Max Born, who is also one of the founders of quantum mechanics. And the Born rule basically states that if you have some state, psi I, and you have some measurement, m sub I, then you can apply this formula to figure out what the probability is of obtaining some output I from this state. So a state, I'm just going to get a little bit quantum mechanical. A state, generally, the way you encode a quantum state is you don't actually have a physical classical piece of information from that state until you apply a measurement. You may have heard that states can occupy this type of state known as a superposition, where prior to a measurement, it doesn't pertain to any specific classical piece of information. So applying a measurement to a quantum state will collapse it to a piece of classical information that we can then use. So the Born rule basically just gives us a formula for what the probability is of obtaining a given outcome of applying this measurement to a quantum state. So specifically this operation, since we know what quantum states are, we know what measurements are, it's basically just a row vector times a matrix times a column vector, which is essentially just an inner product, and that's just going to give you a number. That number corresponds to the probability of obtaining some outcome after you apply this measurement to a quantum state. So that's all we really need to know about measurements, and that's all we need to know about quantum states. So we can kind of move forward now to describing this notion of antidistinguishability. And I think you can describe this in a more rigorous way, but I think conceptually it might make sense to just think about this in the context of this antidistinguishability game or an interaction, because I think this captures the essence of what this is. So the way this particular game unfolds is there's some fixed set of quantum states, which are labeled from psi 1 to psi n. So this is just some artifact of the game. They're just some fixed quantum states that exist somewhere. And then there's two parties. One is known as a referee. The other one is known as a player. So what the referee does is the referee randomly selects one of the states from this collection and hands it to the player. And the referee knows what state they selected, but the player does not know which state they selected from the set. So the player gets the state, and the player is asked by the referee, what state did I not give you? That's the question that the referee asks. And so the player's goal is to determine which state of the set they were not given. So let's just step through a few examples just to see kind of what a correct guess or what an incorrect guess would be in this case. So hypothetically, let's just say that this set of states exists. The referee picks, let's just say psi 1 from this collection of states, and then hands it to the player, and then asks the player, what state did I not give you? So in this case, the referee asks the question, and the player responds with, you did not give me psi 2, which is true because they were given psi 1. So that's an example of a correct guess. And as you might imagine, sort of extrapolating from that, an example of an incorrect guess is when the player responds with the state that they were given. So in this case, the referee sends, again, a hypothetical scenario, psi 1 to the player, asks the player, what state did I not give you? Player responds with psi 1, which is incorrect because he was given psi 1. So this is sort of an example of both a correct and incorrect guess. And this concept of antidistinguishability can sort of be captured by this, where we say that a given set of states are antidistinguishable if it's possible for the player to respond correctly for every one of the states in that set. So if the referee is able to give every single one of the states in a given collection of states to the player, and the player is able to correctly guess which state they were not given for every single state, that collection of states is known as anti-distinguishable. And if that's not possible for the player to do, then that set of states is not anti-distinguishable. So this notion of anti-distinguishability, by the way, is very similar, as you might imagine, to this notion of distinguishability, which is a very big crux of a lot of quantum information research, from cryptography to the foundations of quantum information, to a number of different areas of the whole field. So distinguishability has actually been a very well-studied kind of field, and probably for natural reasons. Anti-distinguishability sort of turns the question on its head. Instead of asking, what state did I give you? The question that we're asking here is, what state did I not give you? So different phrasing, but it has different implications. So maybe a more formal way of sort of capturing the notion of anti-distinguishability is just by this statement here. So we don't need to think about it in the context of a game. We can think about it like this. If I give you some collection of quantum states that live in some d-dimensional complex Euclidean space, then these states are anti-distinguishable if there exists a corresponding collection of measurement operators, M1 through Mn, such that this equation here, which is the Born rule that we discussed before, if that equation is equal to 0 for every single state in the set. So what is that saying? That's basically corresponding to the case where the player is able to respond correctly with the fact that they did not get a certain state. So this is the probability that they're able to obtain this outcome. So there's a measurement that exists for every single one of the states where the outcome of this probability is 0. So if there exists such a collection of measurements where this is the case, then the collection of quantum states are anti-distinguishable. And if there does not exist such a collection of measurements, then it's not anti-distinguishable. So that's all very fine, but why would anyone care about this? This is fairly maybe esoteric, and it's kind of framed in a way where it's just very hypothetical and very theoretical. Like why is this useful? Where else has it been studied? So there's a number of places where this anti-distinguishability idea has been brought up, and here are a few, and I'll kind of talk through a few of these. Some of these are kind of interesting. So one particular result that came out about 10 years ago, which is kind of an interesting result that pertains to the foundations of quantum mechanics, is this notion of this thing known as the PBR theorem. So the PBR theorem, it's named after the names of the authors of this paper that came up with this theorem, and it's basically a no-go theorem in quantum mechanics. So what is a no-go theorem? If you have some background in quantum mechanics, or even if you've seen some popular science stuff around quantum mechanics, you may be familiar with Bell's theorem. And actually, if you're familiar with any of the Nobel Prize winners as of most recent in physics, all of them won the Nobel Prize for this idea of Bell's theorem. Bell's theorem is basically this idea that was come up with by John Bell, who was a physicist in the 60s. And he was thinking about this paper that came out from Einstein and co-authors, who, if you don't know, Einstein was a big opponent of quantum mechanics. So he didn't like quantum mechanics because he thought it was an incomplete theory of nature. He thought that there were these so-called hidden variables that basically, because these things existed in quantum mechanics, you could not call it a complete theory of nature. So him and two other co-authors, Podolsky and Rosen, put together this paper and said, quantum mechanics is not complete, therefore it's not a good theory. And in the 60s, John Bell was thinking about this paper and came up with what is known as Bell's theorem, which is effectively a thought experiment that shows that quantum mechanics does not contain these hidden variables. It is a complete, consistent theory of nature. And it since then has been experimentally verified in the lab, and it's all quite compelling. This PBR theorem is kind of a similar bent on that, where it's also a no-go theorem that has to do with the quantum state itself. Now, the PBR theorem basically asks the following question: is the quantum state epistemic or is it ontological? And that sounds like you're in a philosophy class right now, but basically what it boils down to is the notion of a quantum state, is it a real thing that exists in objective reality, or is it something epistemic where it pertains to the state of knowledge of something? So for instance, a probability distribution doesn't exist in objective reality, but a probability distribution gives you information about something, how certain events will probabilistically occur. Is the quantum state an object like that, or is it something that exists in objective reality? And what's kind of interesting, I'm not going to go into this because the details are a little bit involved, but the crux of the proof to show this thought experiment that indeed the quantum state is something that exists in ontological objective reality, they use this idea of antidistinguishability to get there. That was a big part of the crux of their proof. So kind of interesting for the foundations of quantum mechanics. It's also been studied under a couple different names. Quantum state exclusion is one name that's very commonly associated with, because again, what is antidistinguishability? You're excluding the quantum state. You're guessing which state you were not given. And this whole notion of quantum state exclusion is actually quite useful for cryptographic purposes. So even if you don't have a background in quantum computing, you may have heard that quantum computers offer a big benefit to certain problems. One of the problems is the factorization of very large products of prime numbers, which, surprise, is kind of the basis on which all of the crypto systems today work that are using RSA. So RSA, the thing that, saves your emails and your Amazon transactions, all of that is kind of made secure by the fact that factoring products of prime numbers is difficult to do. That's the hardness of the RSA algorithm. So quantum computers, in theory, can break this in polynomial time, where it would take an exponential amount of time for classical computers to do. So there's this whole field of post-quantum cryptography that basically is coming up with different crypto systems where the hardness of those crypto systems are not based on problems that are thought to be difficult for both classical and quantum computers. So one such scheme in the post-quantum crypto world, this antidistinguishability idea is useful for some attributes of including or extending some of the quantum memory for some of these things, which is kind of interesting too. And one thing that we'll take a look at a little bit later is that antidistinguishability, the ability to determine whether or not a given set of states are antidistinguishable or not, can be framed as a very specific optimization problem. And we'll take advantage of this in a little bit later in the slides. So what is the antidistinguishability conjecture? What is this conjecture? So let's just state it, and then we'll say why it's interesting. So the conjecture itself is fairly innocuous. If you look at this conjecture, it's a fairly basic statement. There's this conjecture that was posed in the paper that's referenced below that basically says if you have a collection of quantum states, a collection of d-dimensional quantum states, then the authors claimed in this conjecture that the states are antidistinguishable if the following equation is true. So if you take the absolute value of the inner product of any two states in the set, if that quantity is less than or equal to this quantity here, d minus 2 over d minus 1 for d being the dimension of the states, if that's true for all of the states in the set, then the authors claimed in this conjecture that this would imply those states are antidistinguishable. So this is a way in which you can determine possibly whether or not a given collection of states are antidistinguishable. So why on earth was this phrased? What is this? What is the purpose of this conjecture? Because on the surface, it's nice. You have another way to determine whether or not potentially states are antidistinguishable, but what does it actually imply? So the reasoning for this is a little bit in-depth and complicated, but generally, if this conjecture were true, it would imply that there exists some quantum communication task such that you could solve the communication task with log d qubits, but it would require big omega d log d classical bits to solve. So what does that mean? That means that there exists some communication task where you get an exponential separation between classical and quantum. And isolating these types of exponential separations between classical and quantum communication or otherwise are always quite nice. It's what keeps me employed. It's what keeps the field kind of moving along. So it wouldn't be the most groundbreaking thing on the planet, but it's always nice to kind of isolate and show these off when they arise. So unfortunately, like I said, this conjecture is not true. So I don't think you get this for free. But let's think about this a little bit, because the conjecture itself, when I saw this in the paper, I thought it was a really nice conjecture, and I thought it was true. And for a long time, I tried to prove that it was true because there was a lot of evidence that it actually was true. So specifically for the cases of d is equal to 2, d is equal to 3, this conjecture was known to be true. And actually, the authors that posed this conjecture provided quite a bit of numerical evidence to indicate that generally this conjecture was true. So for a while, I tried to prove that it was true, didn't have a whole lot of success. And then I tried to flip it on its head and figure out, okay, can we invalidate the conjecture? Let's try to disprove it. So what would disproving the conjecture look like? Well, it would be a little bit easier in some sense, because you would just need to find a counterexample. You need to find some collection of states that are not anti-distinguishable, but do satisfy that conjecture bound. So if you have that, you have a certificate. You've got your ability to say that, look, I found a counterexample, this conjecture isn't true. So in order to invalidate this conjecture, we need some way of like generating a bunch of random collections of states and being able to quickly determine whether or not those states are anti-distinguishable or not. And one way you can do this is through an optimization technique known as semidefinite programming. And if you haven't heard of this technique before, I'll just kind of give like a one slide introduction on what SDPs, semi-definite programs, are. So you may have seen linear programs. If you've taken pre-calculus, you may have seen like that uses an optimization technique. And I should also say that programming here is not meant to be programming in the sense of coding, but programming in the sense of sort of the old school way of optimization. So linear programming by proxy is you're trying to optimize over some objective function according to some linear constraints. So, you know, Farmer Bob has so much fencing, he wants to enclose his animals in, he wants to maximize the amount of enclosure he has. That's a linear programming problem, or it can be framed as a linear programming problem. You have some constraints, they're linear, you're trying to maximize a certain thing. By proxy, semi-definite programs are basically the same thing, where you have a primal dual pair that gives you an upper-lower bound and some problem, but now you're optimizing with respect to positive semi-definite operators. So this is really useful in quantum information for one main reason, is that I would say the main three ingredients in quantum information, two of which we've already talked about, states and measurements. The third is quantum channels. But all of these things mathematically can be represented by positive semi-definite matrices. So if you open up, you know, the archive and you peruse through the quantum information postings, you will find no shortage of usages of this particular technique to frame certain optimization problems in this framework. It's a very useful tool that you know, has a lot of impact in quantum information. It's also got some other benefits too. They're efficiently solvable in polynomial time. They provide nice upper and lower bounds for a given problem if you can specify the problems in this way. And one thing that we'll take advantage of that's kind of neat is that there's a lot of third-party software packages that allow you to specify a problem like this and numerically be able to solve it, which is very convenient. So we'll be taking a look at that a little bit. So given the SDP idea, we can kind of shove and shoehorn this idea of anti-distinguishability in this SDP framework. And actually, this particular primal dual pair is precisely the SDP that characterizes whether or not a given ensemble, a collection of quantum states, are anti-distinguishable or not. So the way that I like to kind of write STPs is generally the primal problem tends to have like a lot of the intuition, or at least in my experience it does. And then when you come up with the dual problem, that's more so just kind of like turning a crank. You've defined your primal problem, and just by kind of rote calculation, you sort of arrive at the dual problem with everything else associated with it. So it's not super insightful to look at the dual for anything that pertains to the problem, at least not in my estimation. If you look at the primal problem, though, you'll see a lot of things that should look pretty familiar based on what we've already talked about. So what are we doing in the primal problem? Well, we're trying to minimize something. What are we trying to minimize? We're trying to minimize this objective function here, which is precisely the condition for which a collection of states are anti-distinguishable. Because remember, if we go back a few slides, the whole idea is that there's some measurements that exist such that this equation is true. So if this is equal to 0 for every single state in the set for every single measurement, then we know that the collection of states are anti-distinguishable. So if I go back here, we're trying to get this guy as small as possible. And if the optimal value of that is 0, then the states are anti-distinguishable. So the input into this primal problem are the quantum states that we're trying to check. Hey, is this anti-distinguishable? And the variables that we're optimizing over in this case are the measurements. So what are valid quantum measurements? Well, valid quantum measurements, like we said, have two properties. One is that all of them need to be positive semi-definite. So the eigenvalues of all of them need to be greater than or equal to 0. And then also that if you have this collection of measurements, if you sum them all up, they should be equal to the identity matrix. So if you have those two constraints, optimizing over those constraints, you're trying to find some measurements that satisfy that condition. So you're going to get a value out of this, which is either going to be 0 or close to 0 in the case where it's anti-distinguishable, or something above 0 in the case where they're not. So this is going to be kind of a useful tool that we can make use of. So we can take that analytic framework of the SDP, we can code it up, in something numeric, so we can actually solve it for a given input of quantum states. And then we can, figure out, okay, is this collection of quantum states antidistinguishable? Is it not? So there's a number of different things that you can use on the market. There's different languages. You can use it in C++, MATLAB, Python, all that good stuff. We're going to be taking advantage of a particular module in Python known as Picos, which is a third-party API to some of these solvers. The reason that this is pretty useful, I think, for quantum information specifically, is because Picos has access to certain functions through their API that are not really used in other SDP solvers, things that are kind of unique to quantum information, like these operations, like these partial transposes and partial traces. They usually only come up in the context of quantum information, but they have support for these things. So it's kind of a nice option to choose. So we'll be making use of that. So before we dive into the code that does this, let's just kind of refresh ourselves about what we're trying to do. We're trying to come up with a counterexample to this antidistinguishability conjecture. So that means we want some way of generating some collection of D random quantum states, which are basically just some D collection of quantum complex Euclidean space vectors. We want to check whether or not those states are antidistinguishable, which again, we can do through this SDP. It'll tell us whether or not they're antidistinguishable. And then if the states are not antidistinguishable, then we check the conjecture condition. So if the conjecture condition is satisfied and the states are not antidistinguishable, we've got our counterexample. So we're good. We're done. We write our paper. We're good. Otherwise, we just keep going until our computer just bursts into flames. And we want to repeat this many, many times. And we also know, again, that the conjecture itself is true in the case for 2 and 3. So we want to skip those cases. We want to go for higher dimensions. So now let's just switch over from the slides into this notebook here, which I'll make a little bit bigger. So this is just, this code is also publicly available. So if you want to, by the way, play around with this, whether it be the notebook or the code that's associated with this, by all means, the links are provided in the slides, and I'm happy to share this offline as well. So even if you don't have any background in Python, I think this should be fairly understandable if you have any background in any kind of programming language. I think it's fairly topical. So I'm going to keep it, fairly high level, and I think it should be fairly digestible. So this notebook basically just goes through pretty much what we already went through in the slides. We've got our imports. We're importing some things that will allow us to create vectors and instantiate the SDPs that we're going to solve, and some basic stuff. The next thing that we do is we actually want to define that SDP. So this is the primal problem that we saw from the slides. So we want to encode this analytic definition of the SDP using this Picos library in Python. And you can see it's kind of nice because this way that you can specify this SDP, I mean, you might have to squint your eyes a little bit, but the way that it's coded up here is kind of a one-to-one mapping in terms of what's actually happening in this expression. So for instance, you're trying to minimize something. You've got your minimization here. You're trying to minimize a sum over an inner product of matrices and vectors. And then you have your constraints where you have these two constraints here, which pertain to these two constraints over here. You want your measurements to be positive semidefinite. You want them to sum up to the identity. So, if you squint at it, it's not too different really. So it's a pretty high level way of specifying SDPs. So we've got our ability wrapped into a function now where we can just call this function, given a list of vectors, quantum states, and this will give us a float, which will basically tell us, hey, is this antidistinguishable or is it not? For completeness here, I've also coded up the dual, but it's basically the same idea. And then just for kind of, cleanness, what we'll do is we'll just wrap this all into like a helper function. So given a collection of vectors, we just return true if the optimal value of the SDP is close to 0. Otherwise, if it's above 0, then we'll return false because it's not antidistinguishable. So cool. So we've got the ability to give it arbitrary collection of d-dimensional quantum states, the vectors, give it into this function, gives us a value, tells us if it's antidistinguishable. Next, we want to deal with the conjecture, which is pretty straightforward to do. So in this case, this is the conjecture. This is the statement of the conjecture. And again, this is just kind of a very naive helper function, which given a list of vectors, you just loop through these vectors and you just check this very basic condition here, which is basically You compute the inner product between these two guys, these two quantum states. It's a very naive for loop, double for loop. And then you get the inner product value. You just check whether or not this condition is satisfied for all of your states in the set. If it is, great, you return true. If there's some state that violates that, you return false. That's pretty much it. The next thing that we want to do is, we check if the conjecture is violated. And in that case, all we do is we basically just wrap those, we put those two functions together. So in that case, we get our vectors, and then we, you want to say hello, Vita?
Hello.
Hello. Say hello to everyone. So we just wrap that into a function, and we just basically just do this. So we check if the inequality is satisfied. We check if it's not anti-distinguishable. This is going to give us an indication, is the conjecture violated or is it not? So then pretty much what we do is we just set however many random examples we want to generate. In this case, I've just done 10, but you ideally want to do lots. You specify the dimension that you want to run it for, and then you just loop. You just loop and you keep checking. You just generate your random vectors, and then you just check, is the conjecture violated or is it not? And you can see in this specific case, running it for 10 examples, no violation of the conjecture. But if you run your computer long enough, you'll probably stumble upon a counterexample. And this is not a unique one, nor is it a particularly pretty one. This is just a very ugly set of 4 vectors that happens to violate the conjecture. So this is one such collection of quantum states that if you plug it in, you will see that it is not anti-distinguishable, but it does satisfy the conjecture. So these are the states kind of explicitly written over here. And then this is kind of the final output. So not a particularly insightful example to look at. If I go back to the slides, we have them right here. Let me just make this full screen again. So this particular collection of states is not like, it's like, okay, great, you found your counterexample, but what's can you do anything about that? You're great at tearing things down. Can you build anything up? And the answer to that is no. So in any case, this is a little bit more about the anti-distinguishability conjecture, where for that particular case of vectors that we found, if we take the largest inner product of any two of those vectors, the largest one is going to be this value here, which is strictly less than the conjectured value of d minus 2 over d minus 1. Whereas the STP value is non-negligibly above a value of 0, which indicates, again, this is not anti-distinguishable, which is a counterexample of this particular conjecture. One ray of hope, I'll just kind of end on here, is that there is some possibility to kind of fix this conjecture. And this is part of some ongoing work with me and 2 other individuals. And we're basically just trying to figure out if there is a way where we can state the condition of anti-distinguishability in kind of a similar type of form, but essentially have it be true instead of just a conjecture. So this statement here is a corollary that came out of kind of a more elaborate theorem that we had that sort of patches up the conjecture. So it's a condition which looks pretty similar to what we saw before in the conjecture, but in this case, this is true for a given collection of quantum states. So what did we see in this talk? Okay, well, we saw anti-distinguishability conjecture for a given dimension is false. There might be some rays of hope to kind of patch that up and study that further. I think what's really exciting, though, is, like I mentioned kind of earlier in the talk, is that the notion of distinguishability in quantum information has been studied quite extensively. There's a lot of content on that. By proxy, anti-distinguishability has not. And I think that there's a pretty green pasture and I think a lot of low-hanging fruit that could be sort of investigated in this realm of anti-distinguishability. And this particular problem, I should say, one thing that's kind of interesting is that the whole conjecture, again, I mentioned that I kind of brushed over why that conjecture even came about. It comes about through all of this analysis of like sphere packing and some theorems of like Claude Shannon from the 30s, and like these really crazy like equiangular triangular frames or equiangular frames, and a lot of these things that are very complicated. SIG POVMs, which is another one. A lot of these very complicated problems that pop up in mathematics and quantum information specifically, and it's all sort of tied into this with anti-distinguishability. So I think that in some way, anti-distinguishability can be used as maybe a tool to investigate some of these things a little bit further, or establish further connections between some of these other really hairy mathematical problems. And yeah, I think it's just generally coming from the space of quantum information, just something that I find particularly interesting and fun to play with. And yeah, I just find it to be maybe selfishly interesting. But that's all I've got to say. So I just want to say thanks again for the opportunity to chat with you, and happy to take any questions.
Awesome. Thank you. Let's thank Vincent.